Okay, so we just saw this example and we computed the Galois group of t to the fourth minus 2 over q. If we were to write out the roots, beta being the real fourth root of 2, if we were to write out the roots of f, we could think of them as vertices of this square, in which case there are some well-known symmetries of a square. One is reflection and the other is rotation by 90 degrees. And so we called sigma, I think I swapped these from the book. I think the book calls sigma rotation and tau reflection, but whatever, it doesn't matter. So sigma was reflection in the real axis and tau was rotation by 90 degrees, and we went through and we proved that sigma and tau define automorphisms. This is it, and they actually give you all of the Galois group. And if you remember your group theory, that's telling us that G is isomorphic to D4 as a subgroup of S4. Now, D4 has order 8. That is not too big, but it's still big enough that there's a lot of subgroups of D4. So we're going to go in and we're going to write out all of the subgroups because we're going to work now on the Galois correspondence, right? So let's now do the Galois correspondence for this example. Okay, so what are the subgroups? I'm going to adopt the labeling convention of the book where I'm switching around the sigmas and taus because I reversed them from what they are in the book. So there are, let's make a table here. It's always bad when someone starts drawing a table. Order elements. We're going to do order elements, and we're going to do name and isomorphism type. Okay, so there's one subgroup of order 8. It's everything. I'm not going to write out the elements. And the name is going to be G, and it's isomorphic to D4. There are several subgroups of order 4. There is the subgroup which is generated by the rotation, which I'm calling tau. Again, this conflicts with the book. Sorry. And the book is going to name that group S. And S, of course, is cyclic of order 4. There is another of order 4, which is generated by reflection and then 180 degrees rotation. Those are commuting operations, and they're both order 2, right? Tau is 90, so tau squared is 180. So tau squared generates a copy of Z2, and sigma generates a copy of Z2. We get Z2 cross Z2. But we can also choose to reflect in a different axis. We can reflect in the I'm not going to be able to think of it right now, but if we look at if we look at tau sigma, that's going to be a reflection in, I believe, one of the diagonals, one of the lines like y equals x or negative x, and this is sort of the same type of group, so we're also going to get this as Z2 cross Z2. And those are all of the order 4 subgroups. And we're not going to go and improve, those are all the order 4, but we're going to take that as a given. Now we have order 2 subgroups. We have the guy that's rotation by 180 degrees. The book's calling that A. Of course, that's cyclic of order 2. All groups of order 2 are cyclic of order 2. We have reflection in the real axis that generates something of order 2, of course. What else? We have reflection in a different axis. We have a different axis. And an even different axis. All right. So these are 5 groups of order 2. And of course, there's only one group of subgroup of order 1, just has the identity in it, and we're going to call that I. Okay, so these are all the subgroups of D4. Again, D4 only has order 8, so writing out all the subgroups, there's not a lot, but there's still a lot. Now we're going to work out the subgroup lattice. So when we work out the subgroup lattice, we're going to use these names. So I, A through E, S, T, U, and G. So I is on the bottom. And then we're going to write them in this order, D, B, A, C, E. All of the subgroups A through E have 1 in them. All right, that's good. Now let's look at the ones that are contained in T. So all the ones that are contained that have elements from 1 tau squared sigma tau squared sigma. So I believe that's A, B, and D. A, B, and D have elements in T. So I'm going to put a T here. All right. Now let's look at S. What guys have elements in S? So elements of S, those are just the rotations. Only A has elements in S. And let's put a U here. U is 1 tau squared tau sigma tau cubed sigma. So that's D. No, that's not D. That's E, C, and A. And of course, all of TS and U are in G. So there is our not so pretty subgroup lattice. Now, this gives us the sort of the dual lattice, the fixed field lattice, where we take the dagger of each of these groups, right? And we know that the Galois correspondence is inclusion reversing. So the fixed field of the identity is going to go at the top now, and the fixed field of the whole group is going to go at the bottom. The fixed field of the identity is just our splitting field, of course, and the fixed field of the whole group is just Q. Instead of now TSU dagger, it's going to be D dagger, B dagger, A dagger, C dagger. I'm going to give myself more space. I don't know why I'm trying to cram it. Right, so that gets reflected upwards. And then we'll put our TS and U below that. D, B, and A all had lines going up to T, so T dagger is going to have lines going up to each of them, and same with the others. So there's our fixed field lattice, and we're going to now go in and find some of these intermediate fields. We're actually going to do that in the next video. The Galois correspondence tells us that these dagger fields that we get by looking at fixed fields, those are all these are all the fields. So this, I say fixed field lattice, I really just mean intermediate extension lattice. We still have to find them, right? We still have to go in and actually compute what they are. We can compute some of them. We know what some of them are just by general stuff. But we have to actually go in and work for these. So we're going to do that in the next video.